You're plugged into the deep dive, and today we're really getting into the weeds on something central to modern AI. We're talking about the mathematical guts of artificial neural networks, or ANNs.
That's right. We're looking at Shiva Narayan Takshila Page's article, Artificial Intelligence,
Oh,
Mathematical Foundations of Artificial Neural Networks, ANNs.
it's a really solid piece. And our mission here really is to pull out those core mathematical ideas, the ones that actually make these things tick.
Yeah, exactly. We want to give you a shortcut, sort of to understanding how AI actually works under the hood without, drowning in equations.
Because once you get a handle on these basics, it really unlocks a deeper understanding of how AI learns, how it sees patterns, makes predictions, all that stuff that can seem a bit like magic sometimes.
Totally. So we're going to structure this around basically four key areas: linear algebra, calculus, probability and stats, and then optimization. Ready to dive in?
Let's do it.
Okay, first up, linear algebra. Right, so linear algebra, you can think of this as the absolute foundation, the scaffolding for ANNs. It gives us the language, the tools, really, to handle all the data. And we're talking vectors, matrices, tensors.
Okay, hold on. Vectors matrices. How do they actually show up in the network? The article mentions input features, weights, biases as vectors.
Yeah, good question. So imagine your input data, right? Maybe it's about a customer, their age, income, whatever. Each piece of info, that's an element in a vector, your input vector.
Okay.
Then that data flows through the network, hits connections between these artificial neurons. Each connection has a weight. How important is it? And all those weights for one layer, you can pack them neatly into a matrix.
A grid of numbers, basically.
Exactly. And then there's the bias vector. That just gives the neuron a little nudge, helps it adjust its firing threshold, more flexibility for learning.
Gotcha. Okay, so the article has this equation, zw.x plus b. Can you, walk us through that with these vectors and matrices?
Sure thing. It's fundamental. X is your input vector, like we said. W is the weight matrix. And like the article says, if you have n inputs and m neurons in the next layer, W is m by n.
Right.
The dot means matrix multiplication. So you're essentially calculating a weighted sum of the inputs for every single neuron in that next layer.
Okay, combining inputs and weights.
Yep. Then you just add B, the bias vector.
Yeah.
And the result, Z, is another vector. It holds the combined score input times weight plus bias for each neuron before any activation.
Okay, so this matrix multiplication, that's what lets the network chew through massive data sets so fast.
Spot on. It's super efficient for doing these calculations across tons of data simultaneously.
Yeah.
And it's doing these linear transformations over and over, layer by layer, well, combined with nonlinear stuff we'll get to.
Yeah.
That lets it learn complex patterns.
And the article really flags the dot product specifically within that multiplication. Why is that so key?
Well, the dot product is the core calculation happening inside each neuron for that weighted sum. Think of it like this. Each weight is kind of asking, how much does this specific input feature matter for the pattern I'm looking for?
Okay.
The dot product then sums up all those answers. How well does the whole input match what this neuron cares about? That's the weighted sum. It determines how strongly that neuron gets activated.
So it's how the network actually starts picking out features, like edges in a picture or words in a sentence.
Precisely. Certain combinations of inputs times weights will result in higher scores, higher Z values for neurons tuned to specific things. That's pattern recognition starting to happen right there.
Okay, linear algebra gives us the structure. Makes sense. Now, calculus. The article says this is crucial for learning optimization, gradient descent, backpropagation. Sounds a bit heavier.
It can seem that way, yeah.
Yeah.
But the core idea is actually quite, well, elegant, I think. Networks learn by trying to get better, right? They minimize the difference between their guess and the right answer. We call this difference the loss. The article uses L.
Right, the error.
Exactly.
Yeah.
And calculus gives us the tools to figure out how to tweak the network's knobs, the weights and biases, to make that loss smaller.
And that's where derivatives come in, the gradient vector of partial derivatives.
Yep. A derivative tells you how a function changes. Here, we want to know how the loss changes when we slightly change a weight or a bias. A partial derivative looks at that change for just one parameter, keeping others fixed. The gradient just bundles all those partial derivatives together into one vector.
Okay.
And crucially, that gradient vector points uphill in the direction where the loss gets bigger, faster.
Right, okay. So if it points uphill, how does that help us get downhill to minimum loss? Gradient descent.
Exactly. We step in the opposite direction of the gradient. The article explains it. You update the weights by subtracting a little bit of the gradient. How much? That's controlled by the learning rate.
Ah, the learning rate, like the step size?
Yeah, precisely. Like finding the bottom of a valley blindfolded, you feel the slope, that's the gradient, and take a step downhill. Too big a step, learning rate too high, you might overshoot. Too small, and it takes forever.
Makes sense. And backpropagation, where does that fit?
Backpropagation is the clever bit. It's the algorithm that actually calculates that gradient efficiently for the whole network, even deep ones. It uses the chain rule from calculus, remember that, to pass the error signal backwards, layer by layer.
Okay.
It figures out how much each weight, way back in the network, contributed to the final error. So you know exactly how to adjust all the weights using gradient descent. So gradient descent says where to go. Backpropagation tells you how to figure out that direction efficiently.
Right, right. Calculation engine for the gradient. Okay. Now, activation functions. The article mentioned sigmoid, ReLU, softmax. What do they do in this learning process?
Ah, yeah, activation functions. They're absolutely critical. They add nonlinearity. See, without them, even a deep network would just be doing linear stuff over and over, basically just one big linear transformation. It couldn't learn complex, twisty patterns in the data.
Because real-world data isn't usually straight lines.
Exactly. So these functions warp the output of that weighted sum. Yeah. Sigmoid squishes everything between 0 and 1. Useful for probabilities, kinda. ReLU is simpler. If the input's positive, output is the same. If negative, it's 0. Very popular, computationally cheap.
Okay.
And softmax. That's usually at the very end for classification. Takes the raw scores and turns them into a nice probability distribution across all the classes. Make sure they all add up to 100%.
So they transform the linear calculation into something more useful for decisions or for the next layer.
That's the idea, mapping those weighted sums into meaningful outputs.
Cool. Okay, so linear algebra for structure, calculus for learning. Next up, probability and statistics. The article says this helps ANNs handle uncertainty. How does that work?
Yeah, this is where things get really interesting, I think. Probability lets networks go beyond just spitting out one answer. They can actually say how sure they are. Think about classification again. Cats, dogs, birds. A softmax output isn't just cat. It's more like 90% chance cat, 7% dog, 3% bird.
Right, a distribution of possibilities.
Exactly. And that uncertainty is vital in the real world, isn't it? Like for a medical diagnosis AI, you really want to know the confidence level.
Definitely. The article also brings up Bayesian learning, BNNs. Sounds a bit more advanced.
It is, kind of, but the core idea is powerful. Regular NNs learn fixed numbers for weights, BNNs. They treat weights as probability distributions. So instead of weight A being exactly zero point 0.7, it might be, say, a range of values centered around zero point 0.7 with some likelihood for each value.
Huh. So the network's knowledge itself is probabilistic.
You got it. Like a doctor giving a range of possible diagnoses with probabilities. The benefits. Big ones. Better understanding of prediction uncertainty, like we said. It can also help stop the model from just memorizing the training data that's overfitting. And they can be great when you don't have much data because you can build in prior knowledge through those initial distributions. It allows for adaptive learning as new data comes in.
That's fascinating. Weights as probabilities. Okay, last piece. Optimization. Making sure ANNs actually find good solutions.
Right. So gradient descent is the basic idea, but there are fancier ways to do it, to make learning faster, more stable. The article mentions SGD, stochastic gradient descent. Instead of looking at all the data at once to calculate the gradient, it updates after just one example, or maybe a small batch.
Faster, but maybe bumpier.
Yeah, exactly. Faster updates, but the path towards the minimum loss can be noisier.
Then there's ATOM and RMS prop. Article suggests they're often faster. How do they work differently?
Ah, yeah, these are adaptive methods. They're clever because they adjust the learning rate for each parameter individually based on past updates. ATOM, for example, uses ideas like momentum, helps it blast through small local minima and keep moving in the right direction, and adaptive learning rates.
So it learns faster for some weights than others.
Kind of. If a parameter's gradient has been consistently large or small, ATOM adjusts its learning rate accordingly. RMS prop does something similar, scaling the learning rate based on a running average of recent gradient magnitudes. These often just converge much faster and more reliably than plain SGD, especially on complex problems.
And loss functions again. The article mentioned mean squared error, cross-entropy loss here in optimization. Remind us how they fit in.
The loss function is, well, it's the target for the optimization. It's the thing we're trying to make as small as possible. MSE, mean squared error, is typical for regression predicting a number. Just looks at the average squared difference between the prediction and the true value. Cross-entropy is the go-to for classification. It measures how different the network's predicted probability distribution is from the actual true distribution, which is usually 100% for the correct class and 0% for others. So the optimizer, like Atom or SGD, uses the gradient of this loss function to guide the weight updates. Minimizing loss means better predictions. Choosing the right loss function is key. It defines what good performance means for the network.
Okay, wow, we've really covered some ground. Linear algebra for structure, calculus driving the learning, probability for uncertainty, and optimization to make it all work efficiently.
Exactly. And you can see, hopefully, how Shiva Narayan Takshila Page's article shows that the power of ANNs isn't magic. It's built on these really solid, interconnected mathematical ideas. Linear algebra gives the framework, calculus provides the learning mechanism, probability handles the fuzziness, and optimization tunes it all up.
So for everyone listening, what's the big takeaway here?
I think it's that, yeah, AI can seem like a black box, but underneath it's running on these mathematical engines. Getting even a basic feel for them gives you, well, a much better sense of what AI can do, what its limits are, and maybe where it's headed.
Right. And maybe a final thought to chew on. As math itself keeps advancing, how might breakthroughs in, say, optimization theory, or maybe new ways of handling probability, how might that change AI in the future? Make it smarter, faster, maybe more reliable?
Yeah. Which of these areas feels like it holds the most potential for the next big leap in AI? That's something to think about.
Definitely. And if you want to dig deeper, checking out that original Tax Sheila page article might be a good next step.
Absolutely. It's a constantly evolving field, and these mathematical roots are where so much of the innovation keeps happening. It's pretty exciting stuff.